There's a lot of argument in the literature. This was thought to be definitely one of its conformations. All proteins will go through lots of different conformations, and it was not argued that this was probably a physiologically relevant conformation for various reasons. Not least of which being, if you've done traffic and transport, any of you done that? Yeah, some of you have done that. This is an ABC transporter, and this is the state in which it binds ATP. So this one's definitely physiologically relevant. There was a question about how relevant this state was, and whether it was an artifact of X-ray crystallography. So, for the benefit, the other graph I showed you looked like this, and the smart people in the room will have looked at that, looked at these three peaks, and thought, oh, there's some sort of, there's a periodicity. Sort of periodicity, an alpha helix. So this looks like an alpha helical periodicity with 3.6 residues per turn. So this bit is definitely an alpha helix, and these residues here, the peaks of these periodicities, are where that helix faces the membrane, faces the lipid bilayer. These troughs are residues where oxygen can't reach. So these troughs are bits where the protein we think is probably very tightly packed. So, so if you've got that far so far, you should be patting yourself on the back or getting the person next to you to give you a pat on the back. So then some smart aleck goes away, and crystallographers are always doing this. Oh, look. So that's from here, this orientation. This bit faces the membrane, yeah? This bit faces, this bit's packed and buried. That's what I mean by orientation. What did you take to mean by orientation? Something subtly different, or? You thought it was a beta sheet. Okay, so a beta sheet would go up, down, up, down, up, down. Whereas this goes, it takes 1, 2, 3, 4, 5. Actually, I'll go from here. 1, 2, 3, 4. So 3 and 4, and then 5, 6, 7. So there's 4 residues from there to there, or 3 residues from there to there. And then from here to here, from that peak to that peak, is another 1, 2, 3. So it's an alpha helical periodicity. If it is beta sheet, it literally just goes like a zigzag. 1, 2, 1, 2, 1, 2. About 6 months after that was done, somebody solved the crystal structure of bacteriodopsin. And so what I've done for you here is shown you the 7 alpha helices in a stick-like representation. And in red are the residues that have been mutated to cystic and probed with EPR spectroscopy. And in the dotted line represents where the membrane is. And then we'll map these on. I've shrunk these down onto one slide for you. In green are the residues that the EPR people said could be quenched by chromium. So they said these residues must be aqueous, and when you look at the crystal structure, those residues fall just on the surface of the membrane. Exactly what you'd have predicted based on here is verified experimentally by a different technique. We then take the residues that showed peaks, showed the periodic peaks for oxygen accessibility. We predict that that means that the oxygen's in the lipid bilayer and can quench those residues because they're exposed to the lipid bilayer, and they are. And then if you take these trough residues here, they're the ones we predict oxygen can't reach, so we need to flip this molecule to see that. If we look down on it from the top, the residues that oxygen doesn't reach are these ones that are, well, they're in yellow, but on yours they'll be in grey, I'm sure, are buried tightly between this helix here and this helix here. And they're buried so tightly that in the time scale of these experiments, molecular oxygen can't get in there and quench them. So for this protein, this technique has told us about local secondary structure, whether something's alpha helical or not, and it's told us about the orientation of those structures, and it's told us about their local chemical environment. I said it could be used to do distance work as well, and I've just got,